Okay, for geometry today, we're doing 7.4 special right triangles. All right, so our objectives say we're going to derive and apply the relationships. We're really just going to apply them. You can look at your book to figure out how to derive them, but there's a lot of things there that we don't really necessarily need to know. But we do need to know how to apply the relationships in 45, 45, 90 triangles, as well as in 30, 60, 90 triangles. All right, so first up, we have the 45, 45, 90 triangle theorem. So this applies to an isosceles right triangle, okay, that has angle measures of 45, 45, and 90. That's why it's called that. So it says, if the length of a leg of an isosceles right triangle is L, so this is the length of a leg. So if the length is L, then the length of the hypotenuse is L times the square root of 2. So label this. It's L times the square root of 2. However you want to write your L, try to get mine in cursive. So it's isosceles. So both of the lengths are the same measure, but the hypotenuse is always going to be the length times the square root of 2. Maybe a cursive L would be better if you want. So example 1 says find the exact values and decimal approximations for the lengths of AC and AB. So let's spend some time breaking down. If this is our right triangle, the hypotenuse is over here. It's always the opposite, the side opposite of the right angle. Okay, so that's our hypotenuse, which means BC and AC are both legs. It's isosceles. Okay, we're assuming, well, it has to be because it's 45 and 45. So these legs are the same length. So AC is equal to BC, which is 3 centimeters. Okay, now AB is that hypotenuse. So AB is going to be equal to the length times the square root of 2. So the length of your leg, remember, so this is going to be 3 times the square root of 2. That's it. AB is equal to 3 times the square root of 2 centimeters, which is the exact value. And then we need the decimal approximation. So if we put that in your calculator, we're going to put the Wabies because it is an approximation. Okay, if we put that in the calculator, we would get out 4.2 centimeters approximately. Okay, so that is one thing you probably want to work on in your calculator if you're not for sure how to do that, is putting in 3 times the square root of 2, because you get 4.2426. We're just approximating to the nearest hundredth. Is fine. Okay, but practice putting that in your calculator so you're ready for that as well. Okay, so it really is that easy today, just applying these relationships. So let's move on down to the next. Oh, this one thing says, notice the sides of a 45, 45, 90 triangle have a 1 to 1 to the square root of 2 ratio. Okay, so if I go back here, right, it was the length and the length and the square root, the length, pardon me, times the square root of 2. So that's just another way of saying that is that they have a 1 to 1 to the square root of 2 ratio. You're multiplying it by the square root of 2 for the hypotenuse. But sometimes that's an easier way to think about it. Okay, so let's look at the 30, 60, 90 triangle theorem. That's up next here. So this time, the 30, 60, 90 triangle, you'll notice we have a triangle in here that has an angle of 30, a measure of 60, and a measure of 90 degrees. So it actually works really great for an equilateral triangle that we cut in half. That's why that one's there. But that's what we've got, a 30, 60, and 90 degree triangle. So if the length of the shorter leg of a 30, 60, 90 triangle is x, okay, so here's my shorter leg. It's opposite of my smallest angle. So if this one is x, then the length of the longer leg is x times the square root of 3. So here's my longer leg. It's opposite of my 60-degree angle. So its length is x times the square root of 3. And the length of the hypotenuse is 2x. So the hypotenuse is opposite of my 90-degree angle. So this one is equal to 2x. All right, so here, notice the sides of a 30 to 60, 90 triangle have a 1 to the square root of 3 to 2 ratio. Okay, so these are the 1 for the shortest side, the square root of 3 times 2 ratio, or to 2 ratio. Okay, we're going to apply that on the back. And our last theorem here is 7.4.3. So the area of an equilateral, that's important, triangle, is the square root of 3 divided by 4 times the square of the length of one side. And the formula is here. Okay, this is going to be helpful if you have an equilateral triangle, but you don't know the height or the altitude in that triangle. You don't actually have to know it because you don't have to use the base times height formula. So that works out really well when you don't have it. So let's flip over and apply these two theorems to our example problems there. All right, so example 3, find the exact values and decimal approximations for x and z. So we're looking for the side lengths, x and z here. So we've got to think which ones are which. Okay, so the easiest way to do this is find your smallest angle. So 330 is my smallest angle. So the side opposite of that is the shortest leg. So this is my short leg. Opposite of my 60-degree angle, okay, is my long leg. And it's going to get kind of messy here. Opposite of my right angle is my hypotenuse. Okay, so those angle measures tell you a lot about these. Okay. All right, so let me clean this up a little bit. I'm going to leave my notes, but I'm going to erase my arrows here. Okay, so if we go back to what we just talked about, it said in that theorem, right, that the length of the short leg, if x is the length of the short leg, then the longer leg is x times the square root of 3. So let me change colors here. All right, so it said if the short leg is x, which is what it is, then the long leg is x times the square root of 3. And the hypotenuse is 2x. Okay, so if we think about that theorem that way, it might help us. Okay, so let's start with the number we know. We know this 12 centimeters here. So we know 12 equals x times the square root of 3, right? That's what we said. The long leg is x times the square root of 3. How would we solve for x? Well, we could divide by the square root of 3, right? So then we end up with 12 divided by the square root of 3 equals x. Well, that's not very helpful necessarily, but if we multiply, okay, we're going to multiply this by the square root of 3 times the square root of 3. Okay, then we're going to get 12 times the square root of 3 over, what's the square root of 3 times the square root of 3? Perfect, it's 3. So that equals our x. That's the exact value. Now we need that decimal approximation. So if you put in your calculator, you're probably going to put in 12 and put the square root symbol, and it gives you a parentheses. Put the 3 inside there and close the parentheses. And then say divided by 3 to get your answer out of your calculator. and you should get, well, the other thing you could do, I didn't think about this, is you can cancel these, right? These would reduce. 12 divided by 3, like we can cancel that out. 3 divided by 3 is 1, 12 divided by 3 is 4. You could also put in 4 times the square root of 3. That's actually the simplified answer that you should do. And so in your calculator, you would put 4 times the square root, parentheses, 3 equals. And you should get approximately 6.9 centimeters is approximately x. All right, so now we've got x, which is this side, our short leg. So now we can solve for 2x. So 2x is going to equal, and let's go back. We need to use our exact measurement, right? So it's going to equal 2 times 4 times the square root of 3. We always want to use the exact, and then we can put it in for our measurement. Or I shouldn't say 2x is going to equal this. This is z. All right, we want z is equal to 2 times our x value. All right, so then z equals 2 times 4 is 8 times the square root of 3 is our exact measurement. And if we put it in the calculator, our approximation is 13.9 centimeters. So we've got our exact as well as our decimal approximations. All right, and let's try our last one, example 4. Packaging shaped as regular triangular prisms provide excellent protection for shipping large prints. So in each side of the prism, if each side of the prism is 5 inches wide, what is the area of each end cap of the prism? Okay, so we've got it labeled. We've got this wonderful prism. We're going to use that theorem 7.4.3, where the area of an equilateral triangle is the square root of 3 divided by 4 times the side length squared. Okay. Because we have the side length of our this side's 5 and this side is 5. And this side is also 5. It's labeled back here, but it's the same length. Okay, so it's an equilateral triangle. So to take this formula, our area is going to equal the square root of 3 times 4 times the quantity of 5 squared. That's our side length. All right, well, 5 squared is 25. So our area is going to equal the square root of 3 divided by 4 times 25. And if you wanted to simplify this in writing it, to get our exact, it would be 25 times the square root of 3 divided by 4 inches squared is our area. Right, because this is 25 over 1, so we're multiplying the numerators. And then for your approximation, the area is approximately, don't forget those wavy lines, 10.8 inches squared. Approximately 10.8 inches squared. All right, that's it for today. Really just looking at the 45, 45, 90, the 30, 60, 90, those special right triangles, and then the formula for the equilateral, the area of an equilateral triangle, if you know the side lengths. Okay. All right. Well, get started on your homework, and I will see you tomorrow.